Hi, everyone. In the first 3 videos of this lecture, we've discussed how to use the substitution rule to compute indefinite integrals. So in this video, I want to talk about how you have to adjust things to do definite integrals using the substitution rule. And the key point I want to emphasize is that the process is almost identical. There's one big difference. With a definite integral, you have endpoints. You're looking at the integral of some function f of x dx from x equals a to x equals b. And that's important. You're looking from x equals a to x equals b. But when you do the substitution rule, you're changing your variable from x to u. So the only difference is when you substitute u, these endpoints will change. Substitute u, you need to adjust the endpoints. Okay, what does it mean adjust the endpoints? It says when x equals a, what is u equal to? And similarly, when x equals b, what is u equal to? Those will be your new endpoints. So this is the kind of thing where it's easiest to get a hang of it with an example. So let's go back to this first example that we discussed, where the function we're integrating is 2 natural log of x over x dx. What did we do in the first video? Well, we let u equal natural log of x. And then we saw that with this u, what we get is du is 1 over x dx. So the integral that we started with, 2 natural log of x over x dx, is equal to the integral of u du, and then we have a 2, have an extra 2. Okay, but the original integral had endpoints. It started at x equals 1 and ended at x equals 2. And we just have to ask, when x equals 1, u equals natural log of x is equal to 0. And when when x equals 2, u equals natural log of x is just natural log of 2. So the original integral went from 1 to 2, and our new integral in terms of u goes from 0 to natural log of 2. Now, we need an antiderivative of 2u du, which we know is u squared. And we're evaluating a definite integral, so we can use FTC2 and see that this is natural log of 2 squared minus 0 squared, which is just 0. Okay, so what was different here? What was different was we had to go through this part where we adjusted the endpoints from being endpoints in terms of x to endpoints in terms of u. So that's one extra step. But we also gained something, which is in all the indefinite integral substitution rule problems that we've seen so far, we have had to go back at the end. We get an antiderivative in terms of u and substitute back to get a function of x. When you apply the fundamental theorem of calculus, you have this antiderivative in terms of u, and you evaluate it at some numbers and take a difference. You don't have to substitute back and ever get a function of x again. Once you adjust the endpoints, you just treat the rest of the problem like your original integral was in terms of u, and everything works out fine. So let's look at another example. Okay, for our next example, we're going to also go back to something very similar to a function that we talked about in an earlier video. We'll look at the integral from 0 to square root of pi of x times cosine x squared dx. So just like in the previous video, I know the antiderivative of cosine of something, sine of something, when that something is x. So I would like to get rid of this x squared so that what I have left is just cosine of u. So that's why I'm going to choose u equals x squared. So then du is 2x dx. And this integral that we started with, x cosine x squared dx, is equal to the integral, well, du is x dx. So what we have, x dx is not quite du. We have cosine u times 1/2 du. And remember, the important thing here is adjusting the endpoints. When x equals 0, u equals x squared equals 0. And when x equals square root of pi, u equals x squared is equal to square root of pi squared, which is pi. So this original integral goes from 0 to root pi, and our new integral goes from 0 to pi. We know an antiderivative of cosine is just sine. So this is 1/2 sine of u evaluated at pi and at 0. So what we get is 1/2 sine pi minus 1/2 sine 0. And this is sine of pi is 0, sine of 0 is 0. So this whole thing is just 0. It's 0 minus 0. For the final example of this video, let's look at a function that looks a little bit different. Let's take the integral from e to e to the 4th of 1 over x times square root of natural log of x. This square root of natural log of x makes me very, very uncomfortable. So what I want to do is choose u so that this piece looks nicer. So let's let u be equal to the thing inside the square root, natural log of x. With this choice, just like in our earlier example, du is 1 over x dx. So now our integral from e to the 4th of 1 over x square root natural log of x dx is equal to the integral of 1 over square root of u times 1 over x dx. That is du. And we have to do this thing where we adjust the endpoints. So when x equals e, u equals natural log of x equals natural log of e, which is 1. And when x equals e to the 4th, u equals natural log of x equals natural log of e to the 4th, which is 4. So we just need to take the integral from 1 to 4 of 1 over square root of x, which is u to the minus 1/2 power. We know an antiderivative here will be 2 times u to the 1/2 power. Because when you differentiate, this 1/2 cancels with the 2, and you get u to the minus 1/2, evaluated at 4 and at 1. So this is 2 times the square root of 4 minus 2 times the square root of 1. Square root of 4 is 2. Square root of 1 is 1. This is 2 times 2, 4 minus 2. And we get 2. OK. So what did we do in this video? We saw that definite integrals with the substitution rule are just like indefinite integrals, except there's this one extra step where you have to adjust the endpoints. On the other hand, when you get an answer at the end in terms of u, you don't need to substitute back in terms of x. So often the challenging thing in applying the substitution rule is choosing what function to let u be equal to. And in both of the examples that you can still see here, we have cosine of x squared. We have cosine of some function of x. And here we have square root of some function of x. So how did we pick u? We picked u to be the inner function. Because when we have one function inside another function, that's the kind of thing that the chain rule tells us about. We would like to take that inside function and make it as simple as possible. So that's really often the first thing to try. If you have an integral that has cosine of some complicated function of x, let u be equal to that complicated function of x. Or the square root of some complicated function of x, let u be equal to that complicated function of x.